So, now I will get away from CUDA and go to CUPY. So, CUDA programming is fun, but it is tedious, right. You need to think of threads, uh, blocks, and then you need to send data, receive, take the data out, and for long big problems it can be daunting. So, people have come up with strategies so that you can, well, you may not get the best performance, but you can get good performance by doing less work. Okay. So, basically you have Python code with or for multi-core or single core, sequential code usually. Typically we want to use a sequential code and put in GPU with minimal change, and you want the code to run. That is a basic direction, in fact lot of companies are working on. So, PhD student or master students have time, well some time, okay, not too much time, to write a CUDA code, but industry they have to finish in 2 weeks, right, some project, a marketing survey. You can't write a new code for marketing survey on CUDA. So, you have a code which you just want to push it in and it should run. So, that is where there are many strategies. CUPY is one such. So, Python code which is running on a single core will run on a GPU with some changes which I am going to discuss. Other strategies use Numba. These are for Python. In Python code you can use Numba, and Numba also gives you more control. So, Numba I seem to like it. In Numba you can do like you can specify thread blocks and number of blocks, grid, all that is possible. So, instead of C you write in Python, and simpler syntax, but you can do quite a bit. So, I do not know how good Numba is in terms of performance. Finally, we need to look at the performance. And third, which I will do in the class, is OpenACC. Okay. This for Python, and this for C, C++. Well, I will work only with C. OpenMP also can be ported to GPUs. Okay. So, but I will not do the porting, but I will do OpenMP just for multi-core. Okay. We will see. In fact, these are OpenACC and OpenMP are very similar, and these are for C Fortran language. Now, NVIDIA is trying very ambitious project called QNumeric. So, there with no change here in all these things you need to make changes in all these 4 paradigms, but in QNumeric Python code should go as is, not only for one GPU, but many GPUs. Okay. These are okay. How is it possible to do all that? Because there are very smart compilers. Okay. So, compiler sees something, then it should be able to figure out that this is meant for GPU and should spit out the GPU code, and also should be clever that it should specify how many threads and how many blocks. In CUDA we were not generating the object code, but we are deciding how many threads, how should I divide the data, shared memory, how should I use it. So, these are difficult tasks. Okay. I mean, not automating this is not easy, especially shared memory. Right. The code may generate for finite difference the global memory access code, the code with version 1 which required global access. So, that is why these codes are not as great, but with no work or with 1 day of work, if you are getting speed up of let us say even 50 is very good, no, compared to your single core, I get 50 times speed up is great. with CuPy, so our experience is with okay, now I can tell you some numbers. So, we have very good code on spectral method, which I am not covering it in this time of the course. Spectral method, which is solving PDEs using finite with Fourier transform. In CUDA, compared to single core of ROM, you get around 3000 speed up, okay, on A100. But CuPy is giving 500 times speed up, and my PhD students are claiming that it can go up to 1500. Well, I mean, we still need to work on it, but 500 we know the number, it is 500, which is great. So, when I said 50 is underestimate, if you do it properly, it required work, but we are able to reach 500. With OpenACC, there is reporting results of 100 speed up. On, well, not in the same processor, okay, please keep in mind. I take this C code which runs on an Intel processor and I push it to NVIDIA GPU. Then GPU versus CPU. These numbers are GPU speed up over CPU, okay, and these are for single GPU, but for multi GPU you need to do MPI, okay, which I will not do it, but you just write MPI to communicate from between one GPU to next GPU, and it can be done now. But the idea of Q numeric is that avoid all this, automate all this process, and the big push is because of AI, okay. So, AI huge data and people do not have time to do MPI and write in CUDA. So, automate this, and there is huge money as well, no? NVIDIA is supplying to Google, to they are making. So, this automated cars, who is going to compute for automated cars? This car is driving, self-driving cars, huge computation. So, the GPUs and is talking with the global server, which is collecting all the data of the traffic. So, all this should be done fast and with many companies. So, that is the idea, okay. So, do it without really writing advanced codes or very labor intensive codes. Okay, so let us look at CuPy, which is a project which some of you are going to do. So, these are the numbers. Well, I think it got cut the bottom part. So, various applications, and CuPy, the speed up is these around 250, 100. Okay. So, I took a snap. So, this is like molecular dynamics simulation, SWIFT simulation. So, you can see the speed up is compared to a Intel processor, it is 200, 100 like that. So, you can look at the website cupy.dev, which has significantly, I mean, good documentation, not great, but good documentation. And do Google, you will find, I mean, you will find help, examples. Yeah, so this is the thing. So, FFT around 200, array slicing, matrix multiplication, SVD. So, some of them are pretty poor. Okay. Of course, you need a big data size. Okay, 100 MB is the speed up is good. For array size of 8 MB is not good. So, this is 8 MB. Standard deviation calculation, I do not know why it is so bad, but it is not very good. So, GPU acceleration using computing with Python. And CuPy, great thing is it will use CUDA libraries. So, you can call CUDA libraries. When I do FFT on GPU, I am not running the NumPy FFT. So, NVIDIA has a CUDA FFT called cuFFT. Okay. So, cuFFT is fast, meant for CUDA, and we can. So, you do not write FFT CUDA for yourself, you import that and you use that function. So, in Python, if I use cuFFT within the GPU, then I will get same speed as the CUDA code, right. If I avoid data back and forth from host to GPU, your code should be doing great if I use only this. Only problem is data division, okay, data division, thread management, block management. That control is less in well, basically null in CuPy. The interpreter will decide how should I divide the data, okay, and which in fact is less headache, but there is a hit in performance, okay. So, in fact, most of the time you just replace NumPy by CuPy and it works. Okay, so let us look at some simple ideas first. We need to send data, you can't simply just send NumPy to CuPy, it will work. Okay, so some simple stuff. So, import CuPy SCP. Okay, in fact, you can do a if statement, and if GPU, then you can use this and else use this. So, you can also write a sophisticated code which makes the code runnable on both CPU and GPU. Okay, so that's some simple trick. We can define an array x CPU. So, this is standard, no, np dot array, but I want to put that in GPU. So, I want to transfer that to GPU. Then it's simple, you use the function as array. Okay, this simple, well, one easy to remember function as array, put this array x CPU and it automatically write on GPU. So, this is like mem copy, okay. So, this is equivalent to mem copy, and I can print it. So, I am the output is here. So, in GPU the number is 1, 2, 3. These are simple codes I tested. Then I can get the data from GPU to CPU. So, it is again a mem copy, but reverse. So, it is CP is running, is a CuPy will run it, no, CuPy is sending the data as NumPy. So, this is a in GPU data and I just say as NumPy. So, it is going to write in host memory x CPU. So, CPU can, by the way, CPU will work with this data, CPU data, and this will be GPU will work with x GPU. Okay. So, data must be in GPU for it GPU to work on it, and I print it, I get the same number. Okay. So, this is a new function, nice function with CP CUDA device 0. So, this is telling you which device to work on. So, if you have more than one GPU, then you can choose which device to work on. So, in NVIDIA gives rather in Colab I get only one GPU. So, I am using number 0 only, but I could have used number 1 and I could have written on that GPU. So, you can work with multiple GPUs with CuPy, and okay. So, this is an example. So, this is supposed to be 1, okay, if you have multiple GPU. So, x GPU 1, I real function is I copy to GPU 0 and take the data GPU 0, copy in GPU 1. So, how do I do that? The function is same function. So, you say with CP CUDA device 1 or device any number 5. Okay. So, that will put on device 5. So, in one node we can now put 8 GPUs. Okay. The idea is to go to 16 GPUs, but 8 GPUs are possible. In fact, there is a box called DGX box, which I did mention in the class. DGX box has 8 A100s, and the new box I do not remember the name. It has 8 H100, okay, which is a new NVIDIA GPU. Okay. So, these are the function you can use it to transfer data from CPU to GPU and vice versa, or GPU to GPU. Okay. So, you want to write a code which runs on both. We have another way to do it, but this is example I took from internet. So, this function can run on both CPU and GPU depending on the where the array x is. If x is in CPU, then it will run on CPU. So, this one runs on CPU. If x is on GPU, then it will run on GPU. is a good function to have, general function. So, xp, it is cp get array module x. Okay. So, it will choose the hardware, then it will give the name of the hardware and then return, well, basically it is doing some math function, log and maximum, okay, between 0 and x. So, the output is here. First one is CuPy, because it is using GPU. So, using CuPy is giving the results. Next one is CPU, right, this is on a CPU. So, is NP array, right, it is NP is NumPy. So, it is using NumPy. Okay. Anyway, these are some simple illustration. So, we can also in a CuPy you can insert a CUDA kernel. So, example is here. So, this is element wise kernel, okay, CP dot element wise kernel. So, this is a C function, well not C function, but it is saying that this operation you want to do it is a CUDA kernel. It is going to, actually it is not a C function, it is going to create a CUDA code. So, you can tell CuPy to make this CUDA code. So, z is x minus y, which is what, x minus x y squared, and the inputs are here x and y arguments. Okay. So, this is the call here, x is x comma 5 and x is a array, a range. So, it is 0 to 9, right, a range 10 will be 0 to 9. So, what I am going to get? So, 0 to 9 is array minus 5 squared. So, the output is here. So, first 0 minus 5 squared is 25, 1 minus 5 is 4. So, this answer. Okay. So, anyway, this illustration to demonstrate that I can put a CUDA code, a CUDA kernel inside a CuPy code. FFT, okay, you can import those libraries and the call is here. So, first I create an array A. So, if I say cp dot random dot random, so this is random number generator within GPU. So, you may recall that for within a CPU np dot random, right. We have done this quite a bit in our codes. Okay. So, but now instead of NP you do CP, CuPy will generate an array of 16 numbers which are random, but within GPU, and I can do FFT of that. They are complex numbers, because FFT requires complex numbers. RFFT requires real numbers, FFT requires complex numbers, and that is it. So, you see it is very easy to use CuPy. You do not need to, I mean, just run this code, you put in host which is connected to GPU like main your server, and write like this and it will run. So, you can also profile. So, in okay, I should in Colab I just do click, but in your server you have to, I think I am not sure just Python function name will work or not, but you may have to do something on that. So, I am not sure, I never run this on a server, but in our for our CuPy code, so you just click and Colab will run. So, profiler is a nice function of CuPy X profiler. It gives you a benchmark. Okay, it gives you the timing basically. Okay. So, I have a function, well right now I am just doing this big array A, which is 256 cube random numbers, and I am doing the sum of these numbers. Okay. So, it is going to take time. So, I use the function called benchmark. This function, it could have been this myfunc here as well, operation and repeat. That means, well, if I do it only once, there are enough fluctuations, right. We saw that when we did multi-threading examples, but if I do 100 times, then average it, then I get better number, right. So, well, of course, do not do 100 for big codes we do not do 100 times, but for test codes we can do 100 times, they are not so big. So, this is output of benchmark. So, it gives you CPU timing 23 microsecond, okay, this is microsecond, US is not US, but is microsecond, it is supposed to be mu s, plus minus 5.484. So, this is error. So, the range is 19 to maximum of 53. By the way, this is a standard deviation. Huh? So, 53 does not mean the error is going up to 23. These are possible, but not very often. And GPU number is 275 plus minus 4.9 and the range is given here, maximum and minimum. Okay. So, there is another way to, I did not know what the unit was, okay, that is why I had to do this. So, execution time in seconds. So, this is the code I found. So, if I use this, well, anyway, you can also use the thing I want to say is this benchmark is gives an object, A is an object, I am sorry, not A, this benchmark gives an object which has CPU time, GPU time and other information. So, I found only the GPU time, then I can say execution GPU, this is the output. So, benchmark A sum. So, this is my object execution GPU and I want the GPU time, only the GPU time, not the CPU time. Then this object GPU dot GPU times, okay, NP dot average. So, this gives you lot of 100 numbers and I average it and you get a number. This is a float number. This float number is in seconds. This one gives you in seconds and that is 0.00280. So, that is when you realize that this is a microsecond. Okay, so, let us do a real function. I will just finish it. Okay. So, this example I have been working, I mean I have been doing it very often for all sorts of parallel applications. Sum of A star B, A and B are arrays. So, to create two arrays, array 1, array 2, random numbers, float 64, double precision, and so here you synchronize the two devices. Okay, I want to time it. So, time function, okay, time dot time, import time, so start time and end time, and what is the function? So, is just see how easy it is. So, first create these arrays in GPU, CP dot and CP dot sum. So, NP dot sum is replaced by CP dot sum and it is array 1 star array 2 and that is it. So, my code is basically 3 lines, this one and this one, rest all are for timing. Okay. So, you see if you have a NumPy code, then just replace NP by CP and you have the CuPy code and you can generate, you do not need to do transfer, if this will generate inside this GPU. Okay, total time is here 0.013 second and this is the total of sum A star B. I am sure you can convert other examples to CuPy and test it out, is just straightforward. So, other issues which I am not covering is streams. In fact, I did not do it for CUDA itself. What is a stream? So, if I do nonlinear term, for some of you are doing fluid dynamics code, u dot grad u. So, I have u dot ux, u dot grad ui, u dot grad uz. So, it is possible that these three can be done simultaneously. So, these are done by stream functions, stream features of CUDA. Okay, it is nice. You have some threads which can do this one, some can do this, some can do that. So, stream is very useful function, but I think we will skip, we are short of time. So, stream is I am not doing it right now. A memory optimization using memory pool. So, this is a function which is which tells you about memory. Other functions are FFT, they have FFT, RFFT, there are more examples, which I am not doing, and other CuPy libraries like you have BLAST libraries, linear algebra libraries. No time. Well, first of all, I am not interested right now, and you use these libraries only when you need them. Well, I use FFT, but I have not been using other libraries like eigenvalue finders, matrix multiplication, matrix diagonalization. So, okay, so let us stop here.